For our next motion example, we look at an airplane flying with and against a jet stream. So for this particular example, we know the rate of the jet stream. The jet stream is 100 miles per hour. Traveling with the jet stream, an airplane can fly 2,400 miles in the same amount of time as it takes to fly 1,600 miles against the jet stream. The airplane's rate in calm air is an indication of how fast would it be going if there was no jet stream at all. So we're going to be looking at its regular you can think of it as like its base speed. The jet stream, when it flies with the jet stream, you can think of the jet stream as a support. And when it's flying against the jet stream, you can think of it as a deterrent and actually slowing the plane down. This example, you will also see examples like this with streams and currents. Bodies of water moving, someone either swimming with the current or against the current. And then sometimes you'll hear it as a runner being phrased as running against the wind or with the wind. Now, if you're doing your own running, you may not notice the wind as much, but for the physics of these problems, you're expecting going with the wind or the current as being supportive and going against the wind or the current as being a deterrent. So we have two different parts of this trip. You have the part of the trip that goes with the jet stream, and you have the part of the trip that goes against the jet stream. And those are going to be the two things that we consider together, against each other, because they're expected to take the same amount of time. So with the jet stream, we're traveling 2,400 miles. Against the jet stream, we're traveling 1,600 miles. That's our D in our distance. Then we look at our rates. Well, if we're traveling with the jet stream, we have our rate in calm air, which we can call X, plus the 100 miles of the jet stream, the 100 miles per hour, of the jet stream. When we're traveling against the jet stream, that's going to slow us down. And that makes sense. I mean, we went a shorter distance in the same amount of time here than we did here, being supported by the jet stream. And again, since they tell us that those took the same amount of time, that's our time fraction for the first part of the trip. That's with the jet stream. There's our time rational expression for the second part of the trip. That's against the jet stream and acting as a deterrent. And we know that those are going to take the same amount of time. So here we have time with, and over here we have time against the jet stream. Again, we have a fraction equals fraction, so we can cross multiply, or you can multiply by the common denominator. It'll get you to the same place. 2400x minus, be very careful with your zeros. We had 2400 times 100, puts two more zeros on the end. That's 240,000. And then the same thing will happen over here. 1600x plus 1600 with two more zeros, 160,000. Subtracting 1600x, adding the 240,000, you can check my arithmetic and my algebra on this. We end up with 800x is equal to 400,000, leaving us with x is equal to 500. Does that make sense as the speed for a plane in calm air? Sure it does. Does it make sense that we could easily check to make sure that our times are the same? Absolutely. We got the number 500 here. We sub it back into the two spots. Over here we have 2,400 over 600, which is 4 hours of flight. And here we have 1,600 over 400, which is also 4 hours of flight. So walking back through this again, we start off with our base formula for time. We knew the two distances. We knew that one of them was with the jet stream and one of them was against, but we knew that they were in the air for the same amount of time. We set them equal to each other, and we get our still air speed. Again, this example, this type of setup will work for situations where you have currents, where bodies of water are moving, and any kind of wind being supportive or deterring towards any kind of motion.